left corner, right corner, that was what we said was for NTU. And in my rush, I grabbed the wrong logo. It should have been the National Taiwan University. I don't remember what we had up there, but this is the school that we were working with. So the CATIA team will be working with NTU.
Yeah.
We won't hold any ask questions, which will be a bit of a problem. Okay, today's lecture, we're going to talk about collaborative design. You were asked to read chapter 19. Hopefully you've done that. It's a fairly short chapter, but I believe has some really good information and content for us launching off on the project that we are launching into, which is basically the design of a RC race car. Now this is not an RC race car. Although if you wanted, you could come up to my office and you could see that car as an RC race car. So there is one sitting in my office and another one at my home that my kids beat to death. But it's, again, a $250 RC race car that you will be working on, trying to redesign or improve the design of it. Today's lecture, however, is talking about real-world problems, okay? Where was the Camaro designed? Do you know where it was designed? Do you know where it was manufactured? Where it was assembled? What are your thoughts? Do you think it was assembled in Detroit? It was designed in Detroit. I mean, that would be your general thinking, right?
I would think that the head group, like the lead group, would be based out of Detroit because that's where headquarters of GM is.
Okay.
But individual parts were probably done China, Mexico, Japan, Europe, all over.
Okay. When was the good, excellent comment? When was the first Camaro kind of built and put on the road? Does anybody know? I think it was 67. I'd have to check that, but I think it was like 67. Where was that 67 Camaro designed? Where was it engineered? Where was it analyzed? Where was it manufactured? Where was it assembled? All of that. Detroit. In 67, that car was designed and built, assembled in Detroit. This Camaro happens to be manufactured right down here in Australia at the Holden manufacturing facility. It is no longer assembled and manufactured in Detroit. It's done in Australia. They had overcapacity, the best costs, the best kind of facilities and plant and everything else happened to be in Australia for the Camaro. Where did the design of the Camaro, the aesthetic design of the Camaro, where did that actually happen? Well, by and large, it happened quite a bit in a GM facility in the Los Angeles area. Okay? Working very closely with the design center in Seoul, another design center in Shanghai, and a design center that was in India. Okay. Where did a lot of the engineering happen for the Camaro? Well, a lot of the engineering happened in Detroit and in Australia. Okay, tightly coupled between those kind of two locations. Where were all of the parts manufactured? Well, a lot of the parts came out of China. A lot of the parts even came out of Mexico. And those subcomponents made their way over to Australia, and in the Holden factory came together to actually make the Camaro. And for some reason, we can get the Camaro cheaper here in the United States by having it built in Australia. So that's a very real world example of what we're dealing with today. Here's another example. So this is Embraer. Where are they located? Brazil. Okay, so they're a Brazilian airplane manufacturer. Where do they make the 170, 190, and 195? Well, if you start reading these countries and the components that they are, it's a world stage that these things have been modeled, analyzed, manufactured, and once they're manufactured, what do they do with them? They send them to Brazil, and Brazil assembles them. Okay. We could put up an example of the 787. We could put up an example of the Airbus 380. We could put up example after example after example that has a similar story attached to it. The idea of a product being developed, designed, analyzed, and everything in one single location may still apply to a can opener, a manual can opener, but it wouldn't apply probably to an electronic can opener, okay? So there are still products that we can think of as being done kind of in our back door. But any product of substance, any system of substance, is really manufactured, designed, engineered, literally all over the world. And so if that is the case, then we as engineers need to think about, especially we engineering students, need to think about what in our curriculum is kind of preparing us to step into a global engineering, design, analyze, and manufacturing world. I mean, does our thermodynamics class help us with that? Does our fluids class, does our machine design class, do any of those classes really help prepare us for doing that? No, the traditional engineering education that was set up around the World War II timeframe has kind of stuck with us. We have these silos of topics that we learn. But there's really not a place that's helping us learn global engineering. Now you would say, well, we're doing capstone. Well, capstone, that concept was developed about 15, almost 20 years ago. And that concept was developed when we still had kind of the ability to design, analyze, and manufacture in our backyard. But in the 20 years since capstone has really come along, the notion of doing it all locally, centered around one conference table, is not the current paradigm. Capstone needs to kind of branch out, use modern collaboration tools, and help the engineering student community learn how to step out and work in this kind of environment. So the NSF study started a couple years ago. They've got attached to this class was an attempt to look at a traditional class being morphed into something that would help instruct how to do global engineering, how to do global design, global analysis, global kinds of manufacturing. A few years ago, this book was published. by the engineering community, grand challenges for engineering. They came up and said, here are the grand challenges. For example, making solar energy more economical, managing the nitrogen cycle, provide energy from fusion, and the list goes on and on and on. If you look at any one of those grand challenges that are facing us over the next 20 to 30, 40 years, certainly your career span, if you look at any of these, you say, gee, this is a problem that we can solve individually and solely here in the United States, or individually and solely here in Brazil, or in Canada, or in any other single country in the world? And the answer is no. These things sweep across state lines, country lines, they sweep across time zones, they sweep across culture. They impact everybody on this globe. And these things, if we don't solve them, we, the engineers, don't solve them, we're going to find that life is not as elegant tomorrow as it is today. We can't just keep living and burning up resources the way we are. So this is out of that book. Governmental and institutional, political, and economic, and personal and societal barriers will repeatedly rise up to impede the pursuit of solutions to these problems. So here's a bunch of engineers saying, here are all the problems, and what are they saying are going to be the things that stop us? Not knowing how to work together. I think that's the summary. We're going to be at war with somebody else. We're not going to understand them, we're not going to like them, we're not going to be able to do engineering with them because we use inches and they use millimeters and we don't know how to make the conversion. Okay? That's in essence what this community of engineers kind of set back, is we need to somehow figure this out. So this again came out of that. Engineers who will be the leaders of the future will need to manage and direct global engineering activities. In a similar way, they said, in order to save the planet, we need technical people who can work in an international environment. And so this class is attempting to give you a brief look into collaborating with other cultures, other groups. This has been researched for a long time.